So that's the agenda today. I assume that you have looked at the video to get at least familiar with propositional logic, which you have seen multiple times, many times in your life. You're just going to see it again with a slightly different twist as to using it as a representation language. So I'm sort of going to go through those and then, depending on the time, we might actually go into transition into either first order logic or probabilistic logic, depending on the time. But either way, the next class, so the next topic would be probabilistic logic, probabilistic propositional logic. Okay. Basically, I spent my entire year figuring out what interesting quotes I can put for the AI class, and for my entire time, I just was stuck with, Monty Python's. How many of you have seen Monty Python? This is Life of Brian, right? Yeah.
That's
no, Holy Grail. This is Holy Grail?
Yeah.
Okay. Why were they rich in the Holy Grail? I think it's Life of Brian. Okay, so, but anyway, so that was about the riches, and I love the fact in this, what also floats on waters, what are very small rocks. The rock is really small, it might possibly float on water. Actually, it is true. If it's really, really, really small, surface tension may be able to hold it. Yes?
There are also types of volcanic rock that do float.
Yeah, there you go. So, there you go. Right. But then, of course, now I have this. I think it's way more interesting and logical piece of art than anything that Monty Python could do. Okay, so that's that. And let me see if I can get this. Okay, yeah, that's of course those are the pictures of the Python logic. Anyway, the other thing is that I learned two very important things about AI in this week. So I wanted to share them with you. One, of course, is, so we keep talking about artificial intelligence. How about artificial wisdom? Are we going to get artificial wisdom anytime soon? And I learned something very interesting. So this was a AI conference in China, in Beijing, and these monks have a robo-monk who provides artificial wisdom. So clearly we have crossed the threshold, So, do you think this monk would not give wisdom? I mean, it's so cute, I want. So Shaoqi tells me that this particular, what's the name of the monastery you said?
Longquan Temple.
Longquan Temple in Beijing. And there are other Chinese students here. They can check whether you're right or not. But so Longquan Temple apparently have highly educated monks. So I guess instead of wasting time just doing prayers to Buddha, they also do AI programming, and essentially they have made the monk. I'm hoping to get this one of these days so that I can provide wisdom myself. I'll get myself some wisdom. So that's first question. The other question is, there's this issue of, we always have this science envy, computer science, and people keep laughing at me when I say computer science, as if, it's like we have this science envy, that they say it's just technology. So the real question is, AI, which start off is part of computer science, is it AI, is it a science or technology? Serious question, right? So that too, I learned an answer to that. So how many of you know Bill Nye? So Bill Nye the science guy, right? Right. So if Bill Nye is doing something with AI, then it must be science, is what I decided. Actually, I was on that program on Tuesday, and it was fun. This is something that's apparently coming in Netflix next spring. Okay, so I think it was great just seeing how even a small program gets made in Hollywood. I don't know how many of you have been there. And I've been told, as part of going to this, I was sent like some release form where they said my union is SAG. I don't know, any of you know SAG? Screen Actors Guild. So I might be up for Oscar or something. Okay, so that was that. So let's go back to less important questions of life. which is logic, and using it for representation and reasoning. That's something that we're going to discuss. So actually, from this part onwards, we are going to, there is this view in AI called declarativism. That is, you basically tell the system what you want in a declarative fashion. Okay, and so the declarative fashion, then the best would be basically just use language. You know, for the longest time we thought of formal languages. One of the formal languages is logic, and then you can write what you want to write in formal logic, and then presumably hope that to use the mechanisms that we have developed for reasoning with logic to actually infer more things given what you have said. And one of the biggest kind of magics in logic, as you saw in the Monty Python and Trump examples, is given a set of premises, can you derive a conclusion automatically? Okay, and so we basically really want to understand this notion of entailment. It's actually a very simple notion, but I just want to make sure that people get it, because essentially what logic computes is it basically computes all the computational part of logic is computing the entailment. Okay, so given a set of sentences in logic, can you tell whether another sentence follows from what you have written? And all that entailment essentially says is entailment is connected to the notion of possible worlds. So whenever you write something in logic, in essence you are saying, and basically you are writing, about your world. Okay, you're saying, in the world I live in, the following sentence holds. Okay, you already know before, from before, that basically if I just say one particular property holds, then essentially I'm talking about all possible worlds where that sentence holds. So really, as I give a sentence in logic, I'm essentially talking about a set of worlds I could be part of. You could be thinking actually at this point about the vacuum world, blind vacuum world agent, where it might not know exactly where it is, which means it is actually in a set of possible worlds. And then it does an action, and then the set becomes smaller or larger. Right? Remember that we talked about? So in general, what logic is doing is, when I write a sentence in logic about my world, then I'm saying of all the worlds that are possible, the one that I live in has this property true. That means if there are like 1 million worlds, only 500,000 of them have the sentence one true, then I'm only in one of these 500,000 worlds. Then I write one more sentence saying, I also know the following other fact about my world. Every time I write an extra sentence, what does it happen? It basically reduces the number of words that are consistent with what I know to be true of my world. Do you see what I'm saying? And of course, you can get into a situation where you keep adding these sentences and the set becomes empty. Okay, just a second. When the set becomes empty, then you say essentially your logical theory is inconsistent. Okay, that means there is no world where it is possible to have all these facts true. So for example, I can say, in the world I live in, A is true. And so basically all the worlds where A is true are still possibilities for me. Then I say, I just figured out that in the world I live in, not A is true. So now you have to take the set of worlds where A is true and take the subset where not A is true. Obviously that would be an empty subset. Okay? When you say A and not A is inconsistent, in essence what you're saying is, there is no possible world that satisfies what I know about the world I live in. Okay? Now the interesting question then is, when the robot basically, or when an intelligent agent writes what it knows about the world, then it basically comes to a small subset of worlds where it is actually possibly present. Now if I ask a particular sentence whether a particular sentence follows, all I'm asking is it true? Is it true that in all the worlds that you think are still possible, this particular sentence is actually holding? Okay, so that's what entailment is. Okay, so we are going to basically look at that from the set theoretic perspective. So there are like two sets here. The process. Okay, you had a question, right?
Yeah. So if you get to the point where you have no possible worlds, what do? You just drop your knowledge base, or you?
In logic, basically, if there is no possible worlds, one of the very interesting questions would be connected to this notion of entailment. When your knowledge base becomes inconsistent, then you can derive anything. You can basically prove anything once your knowledge base is inconsistent. And you actually need to understand why that is the case from the definition that I'm going to give you in a minute. Okay? So in this particular case, okay, there are two sets of worlds. The set inside is apparently the set of worlds that are consistent with all the sentences in the knowledge base. You use this word knowledge base to mean set of all the sentences that you have written in logic. Okay? So this is the small set of words where all your sentences are going to be true. So this is the only set of words that are consistent with everything that you know. Okay, now I ask you, is alpha also true? Given what you know about your world, is alpha true in your world? Okay, as of now you're basically thinking you are in one of these worlds. To be able to say that alpha is true in your world, it better be true in every one of those worlds. Do you see what I'm saying? Normally you tend to think that, the knowledge base will tell you, intuitively some people tend to think that knowledge base will tell you exactly a specific world that you are part of. And then if you want to see whether alpha is true, you just have to check whether alpha is true in that world. But really what happens is most of the time you don't uniquely identify the world you are in. What you write about your world basically just reduces the number of possibilities that are still alive. There is a fancy name for these worlds in logic, it's called models. So the worlds that are consistent with your knowledge base are called the models of your knowledge base. Okay? And the question then is, I'm asking whether alpha is also true in all the worlds where you can possibly be, given what you know about your knowledge base. And if it turns out that alpha is true in this big set, then clearly, if alpha is true in that big set, then clearly it is, so in that case, every one of these worlds are also part of the alpha world. Okay, so alpha actually follows from what you know. The one thing you have to understand is there are other worlds where alpha is true too, but that's not the issue. All I care about is in one of the worlds that I can possibly be in. In every world that I can possibly be in, is alpha still true? If so, then I can just write alpha. Because that's another property that just happens to hold about my worlds. Okay, so that is the notion of entailment. It's just a set theoretic notion of entailment, and that is basically the basis of much of what we do today. Okay, so this definition of entailment is sort of like definition of derivative as limit h tends to 0, fx plus h minus fx by h. Remember that definition of limit derivative? You do a lot more things with derivatives, but in the end, that's the first principles definition of derivative. This is the first principle definition of what it means to do entailment in logic. And everything that we do is computing this entailment fast. Okay, without actually having to compute these sets and putting these crosses. Okay, now here is an interesting question. Imagine if my knowledge base is actually inconsistent. That means no world is consistent with my knowledge base. So this set is empty set. Do you see what I'm saying? There is basically nothing in it. It will be an empty set. Then if I ask you, is alpha going to be true given the world you are in? What would you say? Do you understand what I'm saying? So basically there is no world you are in at all, because there is no actual possible world that is consistent with what you know. So that means the set of models for your knowledge base is empty set. It has 0 models that are consistent with you. But all entailment says is if alpha is true in every model of the knowledge base, then alpha is entailed. That's the definition. Right? That's the definition. So by that definition, do you think alpha is entailed? Yes. This is something that is counterintuitive to many people who get to logic first time. Okay, if you didn't think about it before, in logic, the moment you can have an inconsistent knowledge base, everything can be derived after that. You see what I'm saying? And so this also could make you ask, so one of the issues of course is logic was formulated, this sort of the propositional logic that we'll talk about in a minute, which is a particular type of logic, that was formulated as far back as the time of Greeks. Okay, Socrates, Aristotle were talking about this. Now the interesting question is they thought of logic as providing, kind of capturing the laws of thought. It's how basically you can codify the human reasoning. Okay, that's what they were thinking of. So now of course by this definition, by here itself you should start having questions as to whether or not in fact you believe that you do completely logical reasoning in the technical sense of logical reasoning. Do you believe in things that are potentially inconsistent with each other? Most of us do. Those of you who didn't even raise your hands, you are not reflective enough of what you actually believe in. Okay? So most of us believe in lots of things that are inconsistent with each other. And yet we actually don't assume that everything follows from our beliefs. So to the extent we do that, we no longer follow the technical definition of logical entailment. Because in logical entailment, if you believe A and not A, then everything can be proved from that. Okay? So keep that in mind. It's a very simple definition, but it actually captures everything that you want to know about logic. So that's the entailment. Knowledge base KB entails a sentence alpha if and only if alpha is true in all the words where the knowledge base is true. And if the knowledge base happens to be true in 0 number of words, then alpha is true in all those 0 number of words. Trivially. That's why when knowledge base is inconsistent, when we say something is inconsistent, what we mean is there is no word that is consistent with what is written in this knowledge base. Okay? Now, so keep that in mind. And if you actually understood up to this part, believe it or not, pretty much everything else that we will talk about today can be just derived from first principles. That's it. Okay? Anyway, so the issue, of course, in logic is we are trying to do this entailment without drawing pictures. Just basically write algorithms that will do this entailment for you. They'll take a knowledge base and they'll take a formula and say, yes, the formula follows. This fact follows, or no, it doesn't follow. Okay, that's what you want to be able to do. That's like the basic idea. Okay. Now, we'll look at 2 different ways of doing it. One is directly from first principles, which is essentially you, in effect, draw these pictures. You don't draw it on the board, but you sort of consider all possible worlds. As you saw in the lecture, you basically draw the big truth table. Okay, either actually draw it or draw as much of the part as needed. You wind up drawing the truth table, and the worlds will be rows in the truth table. And then you basically check, all the rows in which the knowledge base evaluates to true. That would be the subset of the worlds where the knowledge base is actually holding. Then you see if in all those rows, the alpha that you are trying to prove, does it also evaluate to true? If it is, then you're done. If not, it doesn't. Okay, one thing, by the way, that as long as we have this picture, it's worthwhile noticing is imagine, so this is M alpha, right? Instead of this, suppose I have M alpha to be like this.
Professor, you're not sharing.
Yeah. What?
Oh, sorry.
Okay, I have it. So that is M alpha. That is the worlds in which alpha is holding? Is alpha entailed? No, right? You understand? Because in some of the worlds you think you are in, alpha is true. But you may be in some of these other worlds, in which case alpha won't be true. Okay, how about this? Still no. Why? This one bad guy. You see what I'm saying? Right? Now, as far as logic is concerned, if even one of the words that are consistent with your knowledge base, suppose a billion words are consistent with your knowledge base, and alpha holds in all of the billion words except one word. So billion minus one words. You really would like to take a chance and say, I think alpha holds. Right? Logic won't allow you to do that. That's why we go to probabilistic logic. So in some sense, if you have 100 words and 99 of them alpha holds, then you would like to somehow say the probability that alpha is true, given what I know, is something like 0.99. That if you start doing it, you're doing probabilistic logic. Okay? But in logic, without qualifiers, okay, essentially it's all or nothing. So you have to be holding in every one of these words. Now, I'll ask something another very interesting thing, at the risk of saying it so myself. Remember, in Venn diagrams, you draw this to say set of all possible words of the word, right? That's the universal set of words. Okay, so now if I were to suppose that is the set of the worlds where alpha is true, and this is the set of worlds where KB is true. Now, what is the set of worlds where not alpha is true? Right? This is the complement of the set. This is all set theory. Right? So if the red thing is the set of worlds where alpha is true, then the whole green thing minus the red thing is the set of all worlds where not alpha is true. Yes? Yeah.
In the future, can you use colors other than green and red as opposed to?
No, yeah, I can, but you can also come earlier, closer and say.
I'm colorblind.
Sorry. Okay, why is red not seen? I don't
He
know.
said he's colorblind.
Oh, I'm sorry. Oh my God.
Yeah.
So I should tell you this story. The guy who taught me Intro to AI, Jack Minker, was colorblind, and we didn't know that. And so you should do what Jack Minker used to do, which is he would wear parrot green pants and bright yellow shirt. He would look fine, and we'll all basically go crazy looking at him, you know. So that's a way to get back at the universe for making, you know, everybody else not colorblind. So, I'm sorry, I didn't get that. Okay. Okay. So let's just, I guess let's. Okay. So in this particular case, everything that I am scratching like that, that's not alpha. Right? That's not alpha. Okay, now I want to ask you this very interesting question. Given KB is alpha entailed. Okay, for him I will draw this in black again. This is, that's alpha. Okay, so given KB is alpha entailed. No, is not alpha entailed. Pat yourself big time on the back. Okay, because in entailment is not Boolean. You can have a situation where neither alpha nor not alpha is entailed. Do you understand what I'm saying? On a given world, if you take any specific x, either alpha is true there or it's false there. There is no in between. Do you understand that? That's why it's called, normally you think logic as truth and false. It's true or false. So everybody thinks that one way you have to prove that alpha is not true. I mean, if you want to try to prove alpha is true, you might think, well, I'll try to prove not alpha and it's not following, so must be alpha is true. Right? And you just learned just now that entailment is not at all that way. So in fact, you can have KB entails, does not entail alpha, does not imply KB entails not alpha. Of course, I'm using this implication sign that I will talk about in syntax in a minute, but you know that's an implication sign. So just because alpha is not entailed doesn't mean not alpha is entailed. Okay? What happened was, in some of the worlds you are living, alpha is true. In some of the worlds you may be living in, alpha is false. So the truth status of alpha is completely undetermined. Okay? This is something that you do have to understand. So there are three values for a theorem. The theorem can be false. The theorem, if you are trying to prove alpha, either alpha can be proved, or alpha, not alpha can be proved, or you can't prove either. Okay? It's very important to understand. And this is just coming from set theory, right? It's just from sets. And if you should never again get confused, because this is like, lots of people have this trouble, that if I can't prove the theorem, then the opposite of the theorem must be true. Nah, that's not true. Okay? Okay, so keep that in mind. So you would try to do the entailment using models. Basically sort of try to draw these, not draw specifically like a drawing form, but truth tables, draw the truth tables and consider the set of worlds where KB is true, and then see if in all those worlds alpha is also true. And that's the way you can prove entailment. Okay? There is another way of doing it. It turns out that model picking works, but it's not very efficient. And I'll explain to you why it is not efficient. In essence, basically it turns out that irrespective of what you want to prove, you have to typically write a huge big truth table. The size of the truth table would be exponential in the number of propositions. Okay? Whereas sometimes you may want to be able to, if I actually, this much you know about logic, right? So if you happen to know, you have something like this, A1 implies A2, then A2 is true, A4 is true, A5 implies A6, blah, 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 and then somewhere right here also I write A1 is true. Okay, now you know this much because you probably looked at either the lecture or you know about logic, that there is this theorem, there is this way in which you can take A1 is true and A1 implies A2 to say A2 is true. Right? When you did that, you used a rule called modus ponens, or the implication rule. Now the problem, of course, is implication rule is actually what it should be doing is it should be doing exactly what the entailment computation is supposed to do. Okay, again take the differentiation idea. Ultimately everything about derivatives, even things like the multiplicative rule of derivatives, for example, everything ultimately has to be proved using the limit h tends to 0, fx plus h minus fx by h. But once you prove it, when I ask you what is the derivative of x power 15, right, you don't quickly start writing the entire, limit. Even worse, if I ask you the derivative of sine x power 15, you don't start writing the limit. You use chain rule, you use the fact that x power n is nx power n minus 1, all these rules together to compute the derivative. When you use those rules, those are sort of inference rules. But whether or not the derivative you computed is right, the final authority is the first principle cycle. Okay, so in logic, things like mod exponents are basically remembering the shortcuts like x power n is an x power n minus 1. Okay, and you have to prove them at least once in your life to be true with respect to the first principles idea. You actually did this. You probably don't remember, but in your textbook it's been proved once. And then after that you just keep using it. Okay, but the advantage of using those rules is otherwise what you have to do in logic is if you have to write a big truth table which includes A1 to A6, then you need 2 power 6 rows. For every theorem, you need to actually fill a 2 power 6 row table. And if I make your life a little more interesting and say that there is up to 1,000, then you have to write a 2 power 1,000 table. But actually this thing is just staring at you. You would like to just right away write the answer. That yes, in fact, A2 follows. But there's only one way of doing it from first principles, which is to write the entire truth table. Okay? So this is why you wind up trying to understand inference rules. But even though you know this is ultimately the first principles way, you try to understand inference rules because they will essentially try to allow you to compute an element in a sort of a more efficient way. Yes?
Why is it not a 6x6 table?
Which one?
The having 6 things, because you only have A.
That's because if you have 6 Boolean propositions, they can be independently true or false. So you need 2 power 6 rows,
Okay.
right? Yeah, as I said, normally, when in doubt, assume 2 power x is the answer. 2 power n is the answer, but that's actually comes space here. Okay, so we'll do this first and then we'll do this. And the interesting thing is things like implication rule that you already know, that's basically a proof theoretic rule. Proving things like this is called proof theoretic inference. Proving things by this is called model theoretic inference. So there's a large number of fun names. This is model theoretic inference, and this is proof theoretic inference. And one of the interesting things is you have to understand how to do this, but essentially in propositional logic, which is sort of the simplest logic we can start talking about, it is actually possible to prove things this way. Even though the tables can become large, you can prove it at least, they're going to be finite. It turns out, if you try to prove things like this in an extension of propositional logic called first order logic, which also many of you know, which has these quantifications for all x and there exists x, it turns out that any first order theory with at least one function symbol winds up leading to a table that is just has infinite number of rows. Which means model theory is out the window. It's not a question of efficiency. You can't do it.